This is Lecture 8B for Calculus 2 on hydrostatic pressure. If you read the physics forum on the internet, you'll see that it's very common to have questions asked about how to calculate hydrostatic pressure. This is the pressure on an objects submerged under water or in a tank filled with some other fluid. So hopefully I have summarized here the basic steps on to calculate these hydrostatic pressures. And there really are two problems. One is fairly easy, the other is more difficult. But before that, your first problem is, as usual, units. Now in these calculus textbooks, including the ones that I've recommended, which are Stewart and Thomas, both of them use a term that I'm not familiar with, and they use a notation that is not very standard. Stewart calls this weight density. The more common term for what he's talking about is specific weight. Okay. Specific weight is usually denoted with the Greek lowercase gamma. Because Stewart and Thomas use other letters, delta and W. Let's dispense with those right now. What we're talking about is the specific weight of the fluid in which the object is submerged, and it's going to be noted with gamma. By specific, we mean the weight, which is a force, another name for force, weight per unit volume, and that's what we mean by specific weight. So it isn't just the weight of, for example, the water. It is the weight per unit volume depending on the units that you're using. To calculate specific weight, it is the density times the acceleration due to gravity. That's in your MKS or SI units. So gamma is the density. Okay, in MKS units this would be kilograms per cubic meter times the acceleration due to gravity, and that will give you your specific weight. Okay, here it is again, specified for both British units and MKS units. Let the density be in kilograms per cubic meter. We are then working in the MKS unit system. Acceleration due to gravity, 9.81 meters per second squared. Then the specific weight has units of newtons per cubic meter, Newton being the MKS unit for force. In British units, the density is in slugs per cubic feet. Here's acceleration due to gravity, 32 feet per second squared. The result is pounds per cubic feet. Pounds is the British unit of force. Of course, if you're given pounds per cubic feet, then you do have specific weight. And we're always going to use gamma for specific weight in this lecture. And I suggest you do that too in your calculations. Here's a table of specific weights. You can find these on the internet or in many handbooks. And they're listed here for several substances: ethanol, gasoline, mercury, seawater. I don't know about this for seawater. I think we usually use 64.2 for seawater, but that's okay. And two units, one's the imperial, the British units, and the other is the SI or MKS units. This is specific weight. It is weight per unit volume. And once we've got past the units problem, now let's look at the definition of pressure and force. Pressure is force per unit area. On the other hand, if you know the pressure and you know the area, you can calculate the total force on an object. When we're looking at pressure being the depth, at some depth d in a fluid, then the pressure is the specific weight of the fluid times the depth. This will give you your pressure, gamma d. For example, what is the pressure under 25 feet of water? The specific weight of water is 62.4. Okay, we're using pounds per cubic meter, pounds per cubic foot rather, times 25 feet. This gives me pounds per square foot. Now that makes sense because force is in pounds, and pressure is force per unit area. So here you see the unit area. When you multiply this out, you will get, in your dimensional analysis, you would have pounds per square foot. This is from your pressure, okay? And then you multiply it by the area, which would be some feet squared, and now you get pounds, which is force. Okay. Here's another example. So you're looking for the pressure under 3 inches of mercury. Well, the pressure is the specific weight of mercury, which is 847. So that's 847 pounds per cubic foot. And I have to multiply it by the distance that you are underwater. It's 1/4 of a foot. And we get 211 3/4 pounds per square foot. So I'm going to erase some of this, some of the marks on here, just so I can highlight just the things that are important. The important calculations right here. Is that force equals pressure times area. Right. And when we're talking about an object submerged in a fluid, the pressure is the specific weight of the fluid, gamma, times the depth at which the object is submerged. Those are the two basic calculations for hydrostatic pressure. Now we're going to state here this physical axiom. An axiom is something that's accepted without proof, and that is that pressure is exerted equally in all directions. So say you are under 10 feet of water. Okay, the pressure at this depth is the specific density of the water, which is 62.4 from the chart given a couple slides ago, times the depth, which is 10 feet, and we end up with a pressure of 624 pounds per square foot. Right. This pressure is exerted equally to the right, left, above, and below this point. All objects, any object above, below, to the right or left, will feel exactly the same pressure from the water at that point. Okay, this might seem surprising that water pushes sideways as well as up and down when the force of gravity is pushing down, but that's the way it is. This is a concept developed by physical experience. We're going to use this in a few minutes. But something we're not going to use is the fact that the pressure will cause an object to move or to rotate underwater. In reality, this will happen. Here, we're going to ignore that. All the objects are going to be stationary. We're only going to compute the force that's on it and not the reaction to that force. Also, the force due to buoyancy is not going to be included here. Now, when you start to do these problems, the first step is to visualize what you're doing. And the cardinal rule is to make a sketch. Make a sketch of any physical situation, or any situation at all that you can make a sketch of, even any imaginary or hypothetical situation. The reason for this is that without a sketch, you can pretty much guarantee that you're lost. With a sketch, a good sketch, especially one where you have put on it your coordinate system, then the solution is often trivial once you've done the sketch. So the cardinal rule is always to draw a sketch. This is not a fine work of art. It is only a hand-drawn sketch of the situation, including the important details, including the coordinate system, and especially including where you are putting the origin of the coordinate system.